Okay, that was intense discussions. So now let's move on to a new presentation. I will try to cover this within 20 minutes. And so today I'm going to present my work, multilingual representation distillation with contrastive learning, under the advice of Professor Philip Cohen with colleagues from Meta AI. So in this work, we are interested in building better corpus for machine translation, because for many low resource languages, they don't have much available training data. So one important thing for building such corpus is sentence representation, which maps the input sentences into high dimensional vectors and by some black box encoders. And one crucial thing here is that we want to have a good encoders for both our source and target languages, and then measure their similarity. If we have a good encoders for both source and target languages and have a good similarity measurement, we can use that to build bytext. If you have monolingual data, and then you can do similarity measurement to build bytext, or you can do corpus filtering, where in a lot of low resource languages, we are able to first of all, find a larger corpus that contains a lot of noisy data. And then if you have a good similarity measurement, you can filter out the sentences which are bad pairs, then use the remaining corpus to train a translation system. And this is a major experiment that we will show in later this presentation. So first of all, I want to cover some important previous work. I think the most widely adopted previous work is this Siamese structure fine-tuning approach, such as sentence BERT. So for example, if you have a pre-trained model as BERT or Roberta or XLM Roberta, you can use them to encode two different sentences, A and B, and by computing their cosine similarity loss or using a softmax classifier to fine-tune their parameters so that we align the representations or embeddings of these two sentences with our model. However, in my previous experiments, I found that it's not very helpful for many low resource languages or extremely low resource languages that are not included in the pre-training languages for those large models, and they just don't generalize well. So in those cases, we switch to another setting, which is called multilingual distillation. But in fact, it's very similar, and it's also formulated in the previous paper called proposed the architecture laser 3, which is shown as here. If we have a source sentence and a target sentence, we can rely on a pre-trained teacher encoder, which is normally for high resource languages, such as English in our case, because it has a lot of data. And then we're trying to distill the information to the student encoder, which is initialized randomly with, for example, transformer encoders, and that encodes a low resource sentence. And then maps them to high dimensional space and compute a cosine similarity loss and use gradient update to the student side to update the parameters. And however, here's a problem. So using this approach, we can already achieve better performance than fine-tuning BERT or Roberta. But for many low resource languages I work on, there are very limited amount of parallel corpus existing, which means that we don't have much data to train such encoder in the first place. So to combat such low resource settings, I resort to two different techniques. The first is back translation, which is already widely used in translation field as a data augmentation technique, where you translate sentences from a source language to the English and then form the synthetic parallel data. However, this requires a translation model to have a really good quality, which is not really the case for many low resource languages. But because we have the newly released NLP model from Meta, which works on like over 200 languages. So I use that model to translate the languages I work on and to create the synthetic data, which works fairly well, as we will show in the experiment later. The other...
Go back to previous slide.
Okay.
So here is the idea that the student encoder is going to be a multilingual encoder, even though the teacher on the right is a monolingual encoder?
Yes, it could be. So in my experiment, in some cases, it's just bilingual, but in other cases,
that's fine.
Yeah.
So the idea would be that you take English sentences, put them to the model on the right, and when you put the same English sentence to the model on the left, of course, you want to get the same representation. That's all right. That's standard student train. But what other language sentence would you put in here? Would you need a parallel corpus? You would put
The student side only takes the low resource languages. It does not take English sentence.
Okay, and in that case, are these two pairs like the sentence?
Yeah, this should be a translated pair.
Good. Okay, so in other words, for this method to work, you already need a seed parallel text.
Yeah. That's why there's an issue with existing corpus because we don't have enough such corpus to train.
So the net result of it will be two monolingual encoders, one for the source language, one for the target, whose representations are for translation pairs.
Yeah.
Got it. Thank you.
Yeah. So previously I already described the back translation method. Now in this paper, we are going to focus on the contrastive learning approach, which is also a way of doing data augmentations to train better representations. And I will describe in details in the later slides. So first of all, just give a quick overview of the language or data we used. We performed the experiments on many low resource languages such as Khmer, Pashto, Nepali, Sinhala, and also 25 extremely low resource African languages that belongs to the Bellu-Congo language family. And for the back translation, for the CB colon, it stands for clean bytext, and the BT colon stands for back translation. For back translation, we use a 1.3 billion NLB dense model to translate the monolingual data from those low resource languages to English and form the parallel corpus. So now for the contrastive learning approach, we're trying to basically use the student encoder to encode the source sentences into a high dimensional representation queue and use the teacher to encode the target as K target and encode other samples such as those negative samples as K1, K2 all the way to for all the target samples. And in general, the objective is that we're trying to train it so that the Q and K target are pushed closer to each other, while Q and other negative representation are pushed away from each other. And we can see that from the visualization using this approach, we get the representation closer for Sinhala and English. So the red dots are the Sinhala sentences and the blue dots are the English sentences. To dive deep into the method a bit. So first of all, the loss we use is a standard info NCE loss, which by computing this loss and doing back propagation, we can make it so that the models align the Q and K target together and push away from Q and K1, K2, etc. And this is very helpful because it only helps the model to learn that which sentences are similar to others, but also helps it to distinguish the good pairs from the bad pairs, which are important for our task, such as corpus filtering, where you really care about how to filter out those noisy pairs. And here, one more details is how we construct the negative samples. Actually, the negative samples is a core of contrastive learning approaches, and there are many different ways of getting negative samples. So one simple vanilla way would be using your current batch and use all the other sentences in your current batch as negative samples, which is shown in the third row in the experiment result here, which we call it laser 3 in batch. And here we adopted the previous paper like Molko momentum contrastive learning, which we use a memory, which is a queue to store the negative samples. The way we do it is we first have a queue that is first in, first out, and we accumulate all the earlier batches target sentences into the queue to form the negative samples. This is helpful because we are not updating the teacher encoder, so we can construct a queue of size like 4,000 over 4,000. Whereas in the in-batch cases, you can only afford a batch size of around 100 because of the GPU memory limitation. And using this approach, we can find that it gives better performance on the downstream task. And so this gives us the reason why it gives a better performance as outlined in previous paper is that it can help us to find harder negatives, meaning that those negative samples which are closer to your target sentences and hard for the model to tell the difference. This would help the model to learn better semantic information to distinguish the pairs. And so I started thinking like, how can we find better negative samples, which is harder negative samples? In such cases, we devised 2 additional mechanisms to do that, which I'll introduce in the next slide. But here from the visualization, we can see that it gives a quite different visualization, where the for some samples they are really aligned to the English sentences embedding, while for others, they are really pushed away. But this is just T-SNE visualization. So we want empirically results to show that it's really effective. So first of all, I would just describe the method a little bit. So for compared to the previous contrastive learning method, here we did two things that are different. The first thing is to disable batch shuffling, which might sound counterintuitive for you, but I'll describe why that's helpful for our case. So we have a queue which serves as a memory to store the previous batches as negative samples, and we want to find hard negatives. One of the simplest heuristic is to find hard negatives is actually sentence length. You can imagine that if a sentence lengths are similar, it's more likely for the two sentences to have similar meaning, at least in the training corpus, right? So we empirically verify this. If you disable the batch shuffling and sort your input training data by their target sentence length, you would have accumulated your earlier batches, such as if you are currently working with a target of sentence length 10, your memory of negative samples would have sentence ranging from like 6, 7, all the way to 10. And those samples can serve as harder negatives. And we empirically verify that by computing an average target similarity score using the target and the whole memory and plot the distribution on the right, you can see that without the shuffling, we have a much wider distribution with sentences with target similarity that located beyond like 0.4 all the way to 0.7. And this is much higher than the approach with shuffling. So this gives us harder negatives to update the model. And in practice, we don't really notice any problem with using this approach for training. Like sometimes disabling shuffling might result in instability for training, but we are using this and for fine-tuning stage and did not observe any issues with that. The second mechanism we added on top of it is called a pre-filtering mechanism with a target similarity. So we notice that in the corpus, sometimes there are extremely similar sentence pairs, such as the example shown here, bring them here to me versus bring it here to me. Those extremely similar pairs might be too hard for the model to tell and give a bad update. In fact, sometimes there are even duplicates or sentences like what is your name versus what's your name. And for those samples, we don't want to use them as hard negatives because they actually confuse the model during the update. So in those cases, we do target similarity pre-filtering mechanism where we compute the target similarity for each target and negative pair, and we disable the contribution for those samples which have a similarity score over a certain threshold. The threshold is just a hyperparameter, and we empirically show that using a threshold of like 0.9 works well in our case. Using a larger threshold like 1.0 would degrade the performance because you allow the contribution from extremely hard negatives. Using a very small threshold like 0.5 drastically makes the model worse because that filters out all the hard negatives, which again proves that hard negatives is very important for contrastive learning. For the time being, I'm going to show just one experiment, but there are many more experiments in the archive paper available online. So basically the baseline is LaBSE system, which use multilingual distillation. We also provide the two additional baseline on the first and second row. The first row is just laser, which is an earlier version of LaBSE that also works pretty well on many languages as a sentence encoder. And WMT best system is because we use the data from the share test of WMT 19 and 20. So WMT best system is the best number taken from all the participants in those 2 years. And LaBSE is our baseline that use multilingual distillation to distill the information from the teacher to student. LaBSE BT is LaBSE that is exactly as the same as LaBSE, except that it also makes use of the back translation data generated with the NLB model, which shows a huge improvement upon LaBSE using the additional augmentation. And LaBSE CO is our approach using the using a memory-based contrastive learning fine-tuning. And notice that this approach does not actually include and in back translation data from laser3 like laser3BT. So it achieves on par performance as laser3BT with the limited amount of clean bytetext. So the self-supervision from contrastive learning itself is very effective. And then furthermore, with the improvements as disable shuffling and pre-filtering, we get better score at 9.05, which achieves the highest average score overall. And in the papers, there are additional experiments over the 25 African languages. In those cases, we actually show that the back translation and contrastive learning can be used together to achieve the best system possible. So that's all for the presentation, and hopefully I covered in time. And is there any question?
Thanks, Stephen. I'll just make a comment. This is just a historical note.
Mm-hmm.
So in the old days when we were doing classification problems, like David Urowski was doing word sense disambiguation, and he was building the first feature-rich models for that. The people would sometimes evaluate on what was called a pseudo-word disambiguation task, which was basically a contrastive task. You'd say, given a context, is the word sandwich or is it telephone?
Okay.
So basically you were like, imagine there's a word, who, and it could mean sandwich or it could mean telephone. So every time you see either sandwich or telephone, you replace it by who, now you try to disambiguate. And somebody, I don't remember who, maybe it was Marty Hurd, wrote a paper saying, you know, you could do better by doing something like this. If you train or evaluate based on sandwich versus telephone, it's not really as good as if it is, say, letter versus telephone, or, you know, two things that you would tend to find in the same context.
Mm-hmm.
This is it sort of reminds me of that. I'm just
Okay.
there's nothing that you should do
Yeah.
differently, except maybe it would be amusing to cite that extremely old one
Okay.
as being like the proto version of trying to find the relevant negative examples.
Mm-hmm. Yeah.
Question. You go back to one of the pictures, keep going. And maybe it was forward, never forward. One of those graphs which you had where you achieved 0.9 was the right ratio.
Oh, this one?
Yeah, yeah. So forget about the translation task. If I just took a whole bunch of English sentences, right?
Mm-hmm.
What is the distribution of their pairwise similarity? Let's just say. And secondly, if I took a bunch of them and paraphrased them using some standard paraphrasing tools, what is it? In other words, could I have guessed that 0.9 is going to be the answer? Because after all,
I see.
what I want to remove are basically duplicates and near duplicates, right? Where I should not just that it's too hard an example. I should not be trying to contrast.
Yeah, so in the teacher encoder here, we use a pre-trained laser. You can, I guess the threshold is different for each architecture,
Yeah.
but overall for the same architecture, I think it's easy to find the best threshold because it works for English, and you can have many sentences to check whether that's a good threshold or not.
Yeah, what I'm thinking is you don't need a blue score. You might be able to get it just from English to say that when there are sentences that mean the same thing.
Yeah, that's true. That's true. Yeah.
0.94.
Yeah, so the blue score might be less sensitive. So using your approach might show a larger margin between different thresholds, I guess.
That also, like, you know, this sort of do the experiment to find out what's a good threshold rather than guess the sensitive.
Yeah.
So this becomes another hyperparameter search.
Yeah.
Whereas if you had some sense of what real meaningful sentences look like, meaning how similar are they, then you can just say anything above this, I don't want to contrast because it's very likely to be a sentence that means the same thing anyway.
Yep. Yeah, I agree.
The other question I had was actually very early. So what could you do if you didn't have enough parallel text driven bootstrap?
So are you talking about like what can we do besides this two approach?
No, no, right here, right? So you're assuming a reasonably good model based on which you'll create the synthetic data, right? Or you're using the NLLB or some such model.
Yeah.
If you didn't have that, is there a good bootstrap?
No, actually, so I was working a team at Meta, so they previously have tried to use statistic machine translation system for those extremely low resource languages to bootstrap, and it doesn't really work. So they forget about that idea until I start to try, until that new model come out, and I try them, and it shows improvement. Yeah.
No, I was thinking more along the lines of like, you know, start with word embeddings. Because it's often possible to get a dictionary, right? Like you can get a
Like a bilingual lexicon induction kind of stuff.
Yes, I'm wondering whether there's a way to bootstrap from a bilingual, like, again, do neural representations. I'm not saying that.
I know. So yeah, I guess there would be an issue with generating sentences in that case, because you only have the word level translation. So you are saying like using the lexicon induction to do word level translation and generate new sentence with that.
Actually, it's close to an idea that Jason and Philip worked on for a few years with Adi. You take English sentences and whatever, let's say I want to work on Swahili. I'll replace any English word which is in my bilingual lexicon with a Swahili word. And try to make a family corpus like that.
Interesting.
Because at the end of it, you're building a sentence vector, right? So it doesn't matter.
Yeah, I guess so. But if you just basically perturb the English tokens with the counterpart, I don't know if the semantic information would be really as precise or correct as a translation system produced. But I guess that could be that should be empirically verified anyway. So.
Because that's what people do when they do code switching.
Yeah, I know. Yeah.
This is the topic of one of the workshops this past summer.
Well, last summer, yes.
They probably have better models for generating synthetic code switch data.
That they do, yes.
One final question. So the results you show are improving on like low resource setting, right? Do you know how it works on like a high resource setting?
Nope. So yeah, we extensively only work on low resource setting. In high resource setting, I guess using like laser 3 itself should be very good if you have enough data. Yeah. 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 Or even like a fine tuning bird. Yeah.